Good evening, everybody, on this April 1st. So it's a great pleasure and honor to introduce Hong-Hao Tu to this meeting. He's an absolute expert in everything that has to do with conformal field theory, but he also has some extremely interesting thoughts on tensor networks, how you can use them, how you can extend their applications, and therefore I wanted to use basically to quote this small joke, because anytime I see Hong-Hao, I meet Hong-Hao, I have to think about the last words of Caesar just before he died. Tu quoque Hong-Hao amicus meus operatur in gluteus maximus retiacula. So the gluteus maximus retiacula is apparently tensor networks. So Hong-Hao, you too started working on tensor networks. So this is, by this, Hong-Hao, please, the stage is yours.
Okay, thank you very much. And first of all, I would like to thank the organizers for giving me this opportunity to present our results. And of course, thank you very much, Frank, for giving this kind introduction. Okay, so today I'm going to talk about DMRG boosted by Gutzwiller projected wave functions. And this is based on several papers and ongoing work in collaboration with several collaborators, in particular Hong-Hao Tu, who was my former MPQ colleague, and also Lei Wang, Yi Zhou. So they are based in Beijing Institute of Physics, Chinese Academy of Sciences, and also Hui Ke was Yi Zhou's student, and also recently with Rongyang Suan, who was a postdoc working with Yi Zhou. And also I would like to thank Jianwei Li and Professor Yang from DEFT and Sun-Sap Li, so from the AMU group, and also Qi Yang, who is a student of Lei Wang. So I will mostly talk about two published papers last year, and also a preprint last year. Okay, so I think in this audience, I don't have to say too much words about the motivation of tensor networks. So I will instead say a few words about Gutzwiller wave functions, which are popular variational wave functions in condensed matter and also quantum chemistry. So in many fields, condensed matter, such as ITC superconductor, quantum Hall systems, spin liquids, people use these wave functions a lot for understanding the physical phenomena in these strongly correlated systems. So here I will just use simple wave functions like this one, which is a projected Fermi C. So here, this CK dagger, so this creates a number of fermions. And for example, this could be a field bands or half field bands. And then this Gutzwiller projection removes some degrees of freedom locally. For example, if we were considering a spin system, spin 1/2, then we could imagine that at each side, this spin 1/2 fermions could have 4 states, so vacuum, spin up, spin down, and doubly occupied sides. But as long as we impose a Gutzwiller projection so that we only keep singly occupied states, then essentially this wave function is a spin 1/2 wave function. But of course here, this Fermi C has to be half field, otherwise this wave function vanishes. Okay, but of course, another important wave function would be a projected BCS wave function. And this was used, for example, by Philip Anderson for understanding the ITC ground state. This was his proposal. And the idea is that we just start from some BCS states and use Gutzwiller projection to which mimics strong correlations of electrons. And this might be a variational ansatz for the TJ or Hubbard type models. Of course, for spin systems, it's also possible to replace these fermionic operators by using bosonic operators. So these are known as Schwinger bosons. So these are very popular variational wave functions for studying strongly correlated systems. And question? Okay, so the general idea of Gutzwiller wave function can be summarized as follows. So we just start from some Fermi C or paired states of fermions or bosons, and these are always fermionic or bosonic Gaussian states. So typically these are obtained from some kind of mean field theories, and local projection, so Gutzwiller projection, is introduced for recovering the physical Hilbert space. And traditionally, these wave functions have been studied using another numerical method, which is known as variational Monte Carlo. And the idea is that these wave functions can be expanded in real space, and the Gutzwiller projection can be implemented explicitly. And for Fermi C, then this would be Slater determinant. For paired states of fermion, this would be Pfaffian. And for bosonic paired states, this would be a permanent wave function. And variational Monte Carlo, so VMC, that's the standard method for studying these wave functions. And okay, so the advantage of this approach is that it's typically physically motivated. One starts with some microscopic Hamiltonian and do some mean field theory. And it's also possible to consider fluctuations above the mean field theory. So this, for example, in high TC superconductivity, this is known as the gauge theory description, so which takes back some of the fluctuations around the mean field or saddle point solution. And in this way, it's possible to build up connection between these wave functions to low energy effective theories, so typically gauge theories. And there's also a drawback of this approach. So typically this is computationally expensive, but of course, if you study determinant or Pfaffian wave functions with variational Monte Carlo, that's not that expensive in the sense that some fast update methods can be used, but still in some cases, for example, a permanent wave function is not possible to compute a reasonably large system because matrix permanent is difficult to compute. And even for Slater determinants and Pfaffians, the computations can still be expensive in the sense that if you compute some like correlation function or variational energy, but you want to recompute something, you have to restart the Monte Carlo procedure. So this can be expensive. And additionally, this approach has rare characterization tools. For example, entanglement measures is not so easy to obtain. Well, of course, Raney 2 entropy, it's possible to calculate via so-called replica trick, but for other entanglement measures like von Neumann entropy or entanglement spectrum, these are not available. Okay, so here I would like to provide a method for converting these parton wave functions or Gutzwiller wave functions into tensor networks, and then I want to compress these tensor networks into metric spark states. And the motivation of doing this is quite obvious. So first of all, metric spark state is very flexible in doing computations and characterizations. And additionally, once we can do that, these physically motivated wave functions are very natural ansatz for initializing DMRG simulations, because DMRG uses metric spark states as its underlying variational ansatz. Okay, so I will go through the methods quickly, and well, so it's quite simple. And here, let's start with the so-called Gutzwiller projected Fermi C. And the idea is that, well, so here we have a Fermi C, including a number of single particle correlation operators. So these are so-called occupied single particle orbitals. And additionally, we have the Gutzwiller projection. And here again, we consider spin 1/2 system for simplicity, and then this D dagger DM single particle orbitals are expanded using the original fermionic correlation operators, and these are known as, well, for periodic boundary condition, these are known as Bloch wave functions, and then here for simplicity, I just use a so-called interleaf representation. That's not that essential, but makes the method more transparent. So spin 1/2 fermions, I put spin up fermion here and spin down fermion here, and then at each side I only have one fermionic mode. And then Each site is labeled by a single index, and these are known as single particle wave functions. Okay, so well, the idea is very simple. We just write this single particle orbitals, the occupied ones, as an MPO. So that's very straightforward because this is just a sum of C daggers. And this is just a bound dimension 2 MPO, and this is a sum. So therefore here, multiplying this matrices, basically we just sum up this 2, 1 entry, and then the boundary vector simply picks up the sum, and that's the single particle orbital. That's of course very simple, and of course if you want to work with, if you don't want to work with fermions, it's also possible to convert this representation into spin representation by using the Jordan-Wigner transformation. And interestingly, actually, we don't have to pay extra price. And in the end, this is still a bound dimension 2 MPO. And that's very simple, just with Jordan-Wigner transformation. And well, so we will extensively use the graphical representation, and this whole thing, this MPO, is plotted like this, and these are two boundary vectors. And at each side, so this physical interleaved side, so we only have physical dimension is 2, so therefore it corresponds to the spin. Well, this artificially introduced spin degrees of freedom, and then, for example, this entry corresponds to virtual bounds here. The index here is 2, 1, and then we select this guy, and the vertical legs are physical indices, and that's an operator acting on a physical hyperspace. Okay, so then with this, the Fermi C wave function can be written exactly as a tensor network as follows. The idea is that we consider the vacuum, and the vacuum in the Jordan-Wigner spin basis, that's just a product of state, and then we just add this occupied fermions, or occupied single particle orbitals one by one, and first act d1 up to dn, and that's it. That's the exact representation of the Fermi C. And of course, in this representation, the physical indices are here. And then if we want to impose the Gutzwiller projection, we just act that here. And let me remind that these two legs corresponds, this leg corresponds to spin up, and this leg corresponds to spin down in the original fermion basis. And in the end, we just project out the singly occupied hyperspace physical states, and that's it. And that's a product of local projectors. And that's an exact representation of the projected Fermi C. And that's exact, but computation is not so easy to carry out in this representation. And what we want to do is to compress this tensor network into MPS. And the most natural approach would be that we act this each individual MPO onto the initial state. And here, for example, if we do this first contraction, then we end up with a 1 electron state, and then do it again, and that's 2 electron states, and do it many steps with capital N. We act capital N MPOs onto the vacuum, then we end up with the Fermi C, and last step we act the Gutzwiller projection, and that would be an exact representation. But of course, this is too expensive, and we cannot do that exactly. And the reason is that we have capital N MPO, and N is of order is the same as the system size, and then the bond dimension here would grow exponentially, and that means we need some kind of truncation in the intermediate steps. And especially since we have so many MPO evolution, and we need a high fidelity compression so that the errors do not accumulate. So that's the crucial part here. And here, if we were using this approach naively, this would break down. And here, let me also emphasize that a crucial point of this approach, a crucial step of this approach is that we could use a so-called maximally localized Wannier orbitals. So that means if we were considering a Fermi sea, then it's also possible to convert these single particle orbitals by using their linear combination. And because fermions, they anticommute with each other, and we look for some look for a new set of single particle orbitals which are obtained by linear combinations of the original ones, and we hope that these guys, Wannier orbitals, they live in a spatially localized region, and this would be useful for our purpose. And here, well, so this is quite popular in band calculations and also quantum chemistry. So that's quite popular there. Here we are, well, so we have a so-called maximally localized. It's actually ideal in one dimension. And here we use a very, very simple approach for doing this. And of course, it's not going to be the the best localized orbitals in higher dimensions, but still we'll see that it works pretty well. And the idea is that we project this occupied single particle orbitals onto the position operator, and then we rediagonalize this projected position operator. So then the eigen vectors of this projected position operator gives us a set of Wannier orbitals. So these are maximally localized in one dimension, but in higher dimensions, they are not that localized, but still they work pretty well, as we shall see. Okay, so then once we have this set of Wannier orbitals, another crucial step is that we arrange them in a proper order. And this order is the so-called left mid right form. And well, so again, this projected Fermi sea, now we use Wannier orbitals. And the first Wannier orbital, so the non-trivial single particle wave function is spatially localized at the left boundary. And the second one, the last one, it's localized at the right boundary. And we expect that, well, so this part, basically, this MPO is acts as an identity on a physical hyperspace. So this is quite important because it allows us to have a slow entanglement growth. So this would substantially suppress truncation error. And we'll see that actually the entanglement is built up gradually. And well, so one very simple example, so 1D tight binding chain with spinless fermions and at half filling, and we see that if we were using the original single particle orbitals, so by filling up the Fermi sea, well, the Fermi sea, so here the single particle orbitals are just energy eigenmodes, so diagonalizing this, and occupy the Fermi sea from the lowest energy ones to the highest energy ones, we see that actually already creates several electrons on top of the vacuum. Then you see that actually the entanglement entropy is large. And that's not too surprising because it's going to be the CFT scaling, which is the logarithmic entanglement growth. But here, if we use the Wannier orbital, but we create the Wannier orbital from left to right, and then we see that after creating half of the Wannier orbitals, so basically from this picture, you see that if we do this first, this one, second, this one, and from left to right, and basically the Wannier orbital in the middle carries a lot of entanglement. And after creating half of the Wannier orbitals, basically the MPS has a large entanglement when we cut the chain into two halves. And then the remaining half MPO evolution would have a lot of truncation errors. But if we do this so-called left mid right, we see that actually entanglement grows very slowly. And in the end, of course, this system size is pretty small. So we end up with the same state. But if we really want to consider a large system, especially those comparable to variational Monte Carlo, so a few hundred sites, then it's crucial to have a low entanglement growth. in order to have high fidelity for this preparation of MPS. Okay, so well, the next example or benchmark example would be the one-dimensional projected Fermi sea. So this is known as the Hordern-Shastri model, or project spinning half electrons, and these are half field. And in this case, it's a nice benchmark example because it has a parent Hamiltonian, and ground state energy and even arbitrary two-point correlation functions can be computed analytically and even for final size systems. And that provides a very nice benchmark example. And here we consider 100 sites, and we compare the variational energy obtained from this MPO-MPS evolution. And the exact results, we see that if we have bond dimension 5000 and the relative error is actually 10 to the power -7. So typically this kind of precision is hard to achieve by using variational Monte Carlo. And here I also want to show a two-dimensional example. So this is the way to construct a two-dimensional chiral spin liquid, which belongs to the Kalmayer-Laughlin class. So this is a half-field Laughlin states on a lattice, and the idea is that we consider a two-dimensional square lattice, and the electrons have only hoppings, nearest neighbor hoppings, and next nearest neighbor hoppings. And next nearest neighbor hopping, I believe it's a complex. And then once you diagonalize this Hamiltonian, it has two bands, and one of the bands, well, it's gapped with two bands, and one of the band is completely occupied, so that the system is half field. And the occupied band has turn numbers equal to 1, and then well, so that's the case on a torus, and then you Gutzwiller project so that we have spin 1/2 wave function. So this is a way for constructing Kalmayer-Laughlin chiral spin liquid. So this has been studied in the past. And we want to benchmark our method, and we want to see whether we could use our method to prepare metric Bragg states starting from this Gutzwiller projected wave functions. And actually, one extra benefit of this approach is that actually we know how to construct a so-called minimally entangled state basis, or so-called annual eigenbasis. And of course, for our approach, we use, well, so we prepared MPS on a cylinder in order to minimize entanglement. So if we were doing that on a torus, that would have a much larger entanglement. And since we want to use these wave functions also for DMRG, so cylinder is the most natural lattice is the most natural geometry. And perhaps let me use some time to explain how to construct this minimally entangled states, because this is also going to be important for understanding why this is useful in DMRG. The idea is as follows. So we put this system on a cylinder, and well, then again we diagonalize the so-called quadratic Hamiltonian of fermionic partons on a cylinder. Then, since we know that the occupied band would have Chern numbers equal to 1, then actually there would be gapless edge states of these fermionic partons. And the way how we construct the two degenerate ground state on a cylinder is that we properly occupy this so-called exact zero mode, because here we see that for single particle momentum minus pi-half, there are actually 4 exact zero modes. So with spin up, spin down, and also one of them localized at the left boundary, and the other one localizes at the right boundary. And for constructing two ground states, the first one is the one in a so-called identity sector. And here we consider spin up and spin down zero modes both at the left boundary, so one up and one down, and that's the wave function in the identity sector. And the other one, we create spin up electron, or our zero modes occupy the spin up zero modes at the left boundary, and we occupy the spin down zero mode at the right boundary. And of course, the single particle states below this zero mode. So all these ones are occupied, so that the system is always half-filled. And in the end, we apply Gutzwiller projection. So these are, of course, suitable for our method, and we could convert these wave functions into metric Bragg states using our approach. And well, so we do that for a relatively large system, which is comparable to variational Monte Carlo calculations. So, but it's on a cylinder with MPS bound dimension 9000. And we see that actually the entanglement spectrum of the wave function in the identity sector, actually we see a nice conformal tower, which belongs to the identity sector of the SU2 level 1 West-Witten model. So this is the this is known as the bulk edge correspondence, which was so this entanglement spectrum, the correspondence of entanglement spectrum and the CFT is a prediction of Haldane. And additionally, in the semion sector, we also see the entanglement spectrum actually follows the corresponds to the conformal tower of SU2 level 1 West-Witten model in the spin 1/2 conformal tower, Kac-Moody tower. And if you compare this, well, the lowest levels, so here there's a doublet, and if you compare this, the distance of this doublet and the lowest states here, and divide that by the ratio here, which is the unit of the CFT, and then actually this ratio is 1/4. So that corresponds to the conformal weight of semion. And theory predicts that this should be 1/4. And here actually from our approach, we see that that's 0.26, and that's pretty close to the expectation. And this shows that indeed our method could be used for computing entanglement spectrum, which would otherwise not be accessible in variational Monte Carlo calculations. So this provides a way to characterize Gutzwiller projected wave functions. And perhaps this is actually an interesting byproduct. And actually, when we were considering this semion wave function, actually we see that, well, so since we are considering chiral spin liquids, we would expect that the degenerate ground state would be a spin singlet, so in both sectors. And here, actually, one interesting byproduct is that actually in the semion sector, we see that this is the wave function which we were using. So spin up semion at the left boundary and spin down semion at the right boundary. And this is obviously not a spin singlet, and it doesn't have a definite total spin. And of course, it's possible to consider another state which has spin down semion at the left boundary and spin up semion at the right boundary. So this state is actually different from this state. And then by using these two states, we can use a linear combination so that, well, so we can construct spin singlet, and these two semions carrying spin 1/2 would form a long local singlet. So this is somehow similar to the AKRT states with a periodic boundary condition. And here, one interesting feature is that, well, so if we were considering SU2 invariant states, we would end up with this state. And once you calculate the entanglement spectrum of these states, and then you cut the system into two parts, basically you have to cut this long local singlets of spin 1/2. And then this provides an extra degeneracy. So then this tells us actually the entanglement spectrum is corresponds to two copies of semion conformal towers. And that's one, well, so entanglement spectrum is supported in this space. One corresponds to this spin 1/2 degrees of freedom, and the other one is cutting here. We have the semion CFT conformal tower. And this was somehow a surprise. And well, so I think before our approach, this was not at least from the Parton wave, from the Gutzwiller wave function point of view, this was not known, but it will have some important implications when one studies topological phases using DMRG with non-abelian symmetries. And actually, this can be made more general. And general situation is that if the anyons here carry a non-trivial symmetry representation, so either linear or projective representation, so in this case would be spin 1/2. And the entanglement spectrum for the minimally entangled state or annual eigenbasis preserving symmetry. So that means we consider a state which is invariant under this symmetry group. Then actually the entanglement spectrum is not going to be the single conformal tower, but it will be a tensor product of the conformal tower with the symmetry representation of the anion. So this was somehow useful insights based on our method. And I think I may go back to this at a later point. And once we use DMRG with non-abelian symmetry, we would always end up with a state, which is either invariant under the symmetry group or corresponds to an eigenstate of the Casimir operator. And in this case, we may not have a clean conformal tower if it's a chiral topological state. So this is the key message here, which is a byproduct of this approach of our method. Okay, so let me also say a few words about other possible Gutzwiller wave functions. So I think I have only talked about projected Fermi C. So for projected BCS, the idea is similar, but there's an interesting trick, and the idea is not to consider not to start the wave function from here, but actually this BCS state can be viewed as the ground state of some quadratic Hamiltonians with pairing. And in this case, actually, it's better to use the so-called Bogoliubov cos-particle operators to prepare the BCS, to prepare the MPS. And the idea is that we have the quadratic Hamiltonian, we diagonalize that, and all these eigenenergies of Bogoliubov cos-particles are negative. Then that means the BCS state is actually the fully occupied state of this D dagger, so this Bogoliubov cos-particles. But here we have to create that on top of the vacuum of this D fermions. And actually, since we have pairing, this vacuum of Bogoliubov cos-particles is non-trivial. It doesn't have to be the vacuum of original fermions, but here actually we see that in this formalism it's fully occupied. So therefore, as long as the original vacuum has a non-trivial overlap with this new vacuum, so namely they have the same Fermi parity, then we can also create all these Bogoliubov cos-particles on top of the original vacuum, and then that's the same state up to some constant. And this is crucial for having this MPO MPS evolution, because we want to start with a simple product state as the initial state. And again, here is since this D dagger M, so they satisfy standard fermionic commutation relations, it's possible to use the so-called Wannier trick. You can use their linear combination so that this operator is supported in a spatially localized region, and then the same method would apply. Okay, so let me also comment on the projected bosonic paired states. So this, yeah.
Danke für den Rückruf. Wie geht's?
Okay, so for projected bosonic paired states, this is a very interesting point, because actually variational Monte Carlo does not apply to this case. Well, it applies, but to a very small system size, roughly 40 size, so that the permanence can be computed, can still be computed. And then actually, I would say that our method applies, by writing this pair creation operators as an MPO. So I spare these details, but the idea is that we can write that as a this MPO MPS tensor network, but we have operator creating all pairs involving a particular site. And unfortunately, in the bosonic case, the Wannier trick doesn't work. And in this case, if this pairing function is long-ranged or decays slowly, then we would expect that this kind of MPO MPS evolution has large error. So we have done some calculations, and it shows that actually it's definitely worse than fermionic cases with the Wannier trick. But still, it's fine in one dimension with some power law decaying pairing functions. But in higher dimensions, we haven't done that, but we expect that there will be larger errors, and it's not obvious, it's not clear at all whether this is going to be a practical method. Okay, so recently, and actually, well, actually even several years ago, Fisherman and Steve White, actually, they have considered a closely related situation, and their goal was to study how the fermionic Gaussian states can be compressed into MPS, and of course, one of the motivation is to use the states to initialize DMRG. So that's one of their motivation for developing this approach. And quite recently, there have been several papers on related topics, like one by Norbert, and also from Gardner Chen and Brian Clark's group. And they developed the methods from different viewpoints. And basically, they have used the fact that the reduced density matrix of fermionic Gaussian states can be computed exactly using the correlation matrix trick. And additionally, one could also use the so-called Gaussian DMRG and optimize MPS, which is Gaussian MPS, and that this provides alternative approaches. For example, this third paper by Gardner Chen and Brian Clark's group, so their approach is also very transparent. The idea is that you have this wave function, and you can consider to cut the system into, for example, here 3 parts, and here alpha and beta form orthonormal bases if we have a canonical form. And actually, the support of this alpha, well, this alpha can be chosen to be the eigenbasis of the reduced density matrix, as long as the wave function is Gaussian. And then this matrix, MPS matrix, is basically the wave function overlap of this beta and alpha tensor product n. So this, since for Gaussian states, at least for Slater determinants, this overlap is very simple to compute using Wick's theorem. So it's just a determinant, and that can be computed quite efficiently. And well, so there are indeed some other methods in the market, and well, so then once Gaussian states are prepared, Gutzwiller projections can be performed very easily, like our approach. Okay, so so far I have only talked about how to prepare the states, and of course, once these states are prepared, then it's immediately clear that we can use them for DMRG calculations. And again, I want to use one example to show that indeed there are some benefits for using these wave functions in DMRG. And here one example is this so-called Kitaev's honeycomb model. And this is a nice example because the ground states, well, the eigenstates can be solved exactly, and we can use that for benchmarking traditional DMRG and Gutzwiller wave function boosted DMRG. And well, so this is the Hamiltonian, and one crucial feature of this Kitaev's honeycomb model on a cylinder is that it has a conserved quantity, which is the so-called Wilson loop. So this purple line, this is denoted by C. And here, if you consider the product of this sigma y operators along this closed loop, that's going to be this phi y. So that commutes with the Hamiltonian, and its eigenvalue is +1 or -1. So this provides a label for topological sectors. And here we use a 6x6 cylinder to benchmark how this traditional DMRG and Gutzwiller-boosted DMRG works. So by the way, the ground state of this Kitaev's honeycomb model can be formulated as a Gutzwiller-projected BCS. So of course, it would be unfair to compare if we were preparing this ground state very reliably using our method. So here we start with preparation, which has large error. So basically we start with a very small bound dimension to prepare the states, so that actually it has large error. So I think we start here with a bound dimension 200 to prepare the ground state, and then start from this state to do DMRG sweep, so two-side update to optimize the state. And here the red line is, well, we initialize the DMRG using random MPS, and we see that actually it requires a large number of steps and even a larger bound dimension to converge. And here with Gutzwiller-boosted DMRG, actually we can reach much lower energy. So by the way, there are two lines here, and here we see that actually one of this line corresponds to a state in a phi y equal to +1 sector, and the other one corresponds to phi y equal to -1 sector. So that means actually we can target the ground state of two sectors at the same time without extra effort. So basically we prepare a Gutzwiller wave function in two different sectors, and DMRG sweeps, and it still this good quantum number is still preserved because we are working basically in the subspace. And here we see that another interesting feature is that actually traditional DMRG is trapped into local minima, because actually it goes into a wrong sector, and the ground state, I believe that's in the phi y equal to +1 sector. And actually with many different random MPS initialization, we see that actually the traditional DMRG is trapped into the phi y equal to -1 sector, which is the wrong vacuum. And even in the wrong vacuum, it has well, the error of this of the ground state energy is roughly at least 1 order or almost 2 order of magnitude larger. And we see that actually Gutzwiller-boosted DMRG is efficient and accurate. But of course, you may say that this is a bit unfair in the sense that we more or less know what is the true ground state, and we could prepare from there. But of course, the point of using this Gutzwiller-boosted DMRG is that we need some correct guess. Otherwise, we will not benefit from this approach. Okay, less trivial example would be Kitaev honeycomb model with 111 field, and this model is no longer exactly solvable, and there were some claims that this might be relevant for the recent claim that there is a field-induced spin liquid in alpha ruthenium trichlorides, but in any case we want to use it for benchmarking the method, and actually there were some wave function proposals, and there were some claims that for intermediate fields there's a gapless spin liquid. But of course, in two limits we know the result. For example, h equal to 0, that's solvable. For small h, we are going to have a easing topological phase, and for a very large field, of course, it's the system is completely polarized. And we are going to, oh, I think it's in the wrong order. Okay, so I think we prepare several wave function proposals. So Kitaev's non-abelian spin liquid states, and some proposal from a previous paper, so claimed to be gapless spin liquid states. And we use two quantities to quantify whether these wave functions are good or not. So one is that we consider a wave function from a converged DMRG, and we also consider the wave function proposals. So we can prepare that as an MPS. And of course, on a cylinder, we could compute the wave function overlap. But this might suffer from some issue because we have open boundaries. So this might be a bit artificial. So we also compute the fidelity of the reduced density matrix in the middle of the cylinder. So that provides another way to quantify whether these tri-wave functions are good or not. And here we see that actually for small fields, actually Kitaev's originals, well, non-abelian liquid states, that's a very good ansatz. But when the field is larger, then all these wave functions do not work well. And for larger fields, actually projected, well, fully polarized states, or actually surprisingly also a projected partially polarized state with a non-zero Chern number, basically after Gutzwiller projection, they corresponds to the same state, but in the middle, so both fidelities tell us there are no good variational ansatz. So this shows that actually we can use this approach for quantifying whether some proposed wave functions are good or not. So this in the past, variational Monte Carlo community and DMRG community, basically they are somehow disconnected. And with this recent developments, it seems that we could unify these communities. Okay, so here I think my time is more or less up. So let me summarize and give some outlook. So I have shown that we have now a very simple method to convert Gutzwiller projected wave functions into MPS. And well, the efficient ones are Slater determinants and Pfaffians. So this come from projected fermionic wave functions. For projected bosonic wave functions, we have a method, but we believe that the accuracy is going to be worse, but it's still to be checked, especially in higher dimensions. And we also hope that there will be some better methods. And also I have provided some benchmark examples. So this shows that actually the performance of DMRG can be boosted using these wave functions, Gutzwiller wave functions, as the initial ansatz. And this combines the advantages of both MPS and Gutzwiller wave functions. So first of all, if the ansatz is cleverly chosen, correctly chosen, then we would expect a faster convergence and higher accuracy, as shown for the Kitaev's honeycomb example. And additional interesting thing is that it's possible to preserve topological sectors. So once you prepare the Gutzwiller wave function in the correct sector after some DMRG sweeps, actually it's likely that the converged wave functions stay in these topological sectors. So this was a difficult part in DMRG when studying topological phases. So we have to target several states, and there is no guarantee that you can find the states in the annual eigenbasis sector. And additionally, this offers the possibility to compare the wave function proposals with the DMRG results. So we can quantify whether guessed wave functions are good or not. So this might be useful for some ansatz for TJ models. Okay, so let me also give some outlook. So definitely we would like to see whether this provides some new insights into some challenging models. So there were many models in strongly correlated systems which have elusive ground states like Kagome, Hubbard, TJ, and one example would be Kagome. We don't know whether the ground state is a gapless Dirac spin liquids or Z2 gapped spin liquids or something else. And it would be interesting to revisit this problem using the new approach. And for example, here there are some preliminary results For example, here we have prepared a Dirac spin liquid ansatz from the proposal by Yan and Collaborators, and this was supposed to be the lowest energy projected wave function for Dirac spin liquids. And we see that actually with our method, we can prepare, convert the state into MPS with a high fidelity. So here this shows that how this wave function overlaps goes if we increase bound dimension. So this is a smaller bound dimension, this is a larger one. And if we do this preparation with different bound dimension, and in the end, this overlap, well, of course, absolute value. So this converges to 1 for some bound dimension, then we say that this is a good preparation. So roughly we see that for a reasonably large cylinder, actually bound dimension 10,000 would be enough. And that's a very good fidelity. And we can use this converged states for, first of all, we can use that for initializing DMRG, and we can also compute the converged state, for example, overlap with this states, and check whether this Dirac spin liquid is really close to ground state or not. And well, some preliminary results shows that actually this best Dirac spin liquid states doesn't seem to be a good ansatz, in the sense that, first of all, even if it has a very good variational energy, still when we use that as initialized ansatz in DMRG, it has a slow convergence. So it doesn't perform much better than random states. Then this gives us some indication that this might not be the correct ansatz. But of course, this is just preliminary results, and more CAF studies will follow. And there are also some other directions which I personally find interesting. For example, along this direction, it would be important to understand how minimally entangled states or annual eigenbases can be constructed by using Gutzwiller projective wave functions. So this was, well, some examples. Well, for some simple examples, it's known how to do that, like the Kalmayer-Laughlin, and for many others, actually, we don't really have a systematic method for constructing minimally entangled states. For DMRG studies, this would be a very useful development. And of course, other interesting directions would be how to formulate this formalism in a continuum. Then, well, we know that for many fractional quantum Hall wave functions, they can be written as conformal phase theory correlators, but many others cannot. For example, Jane's composite fermion and composite fermion states, and it would be nice to understand how to formulate a continuous version of this MPS compression for this projected wave functions. So that would be useful for fractional quantum Hall community, and maybe also for field theory studies based on continuous MPS. And additionally, it would be nice to find out how to convert projected Schrödinger boson wave functions into MPS. So basically, this was many people have used Schrödinger bosons to construct mean field ansatz, but Gutzwiller projection based on this bosonic states is more or less unexplored area. And another interesting question would be to develop a method for converting Gutzwiller wave functions into PEPs. So that's also useful for the PEPs community. Okay, that's all, and I think I could stop here, and thank you very much for your attention.
Thanks a lot, Hong-Hao, for this very nice and inspiring talk. I'm sure there are questions. So maybe I can start with a question. So in the beginning, you said, okay, if you work with these Gutzwiller projections, the standard method is basically a Monte Carlo or variational Monte Carlo methods. So how does actually the computational cost compare? Because of course, also these variational Monte Carlo methods, well, they run lots of CPU hours. So is there somehow the size of the system and the computational cost similar, or which one of the two methods kind of wins with respect to like CPU hours?
I don't think I have a comparison for determinant and Pfaffian fast updates. The computational cost scales like O(n) square. So, well, if you do it naively, this would be O(n) cube, but fast update allows O(n) square. And well, so for Monte Carlo, of course, you have to use many CPUs, but if from my point of view, if you can convert that into MPS, you can save it in the hard disk. And then for computing many other quantities, you don't have to rerun this procedure. But for Monte Carlo, you have to rerun this procedure. So from my point of view, I think if there's a reliable MPS compression approach, I think definitely it would be better than the variational Monte Carlo. But I don't really have numbers in mind.
I see that Steve has a question.
Yes, thanks for a very nice talk. It's a nice approach. I wonder if you have any experience yet with partial projections for fermion models. Is it as effective as it is for the when you go all the way to the pure spin models?
Yeah, that's a very good question, and maybe I could go back here. And comparing partial Gutzwiller projection and full Gutzwiller projection, I think the only difference is that here, well, so since here I have the interleaf representation. Actually, well, maybe I could. Oh, sorry. I think the only difference is that here you can block two legs together, or basically block this tensors together, and the physical dimension here, you only have to keep track of bond dimension, the physical dimension 3, because doubly occupied sites is doubly occupied states can be already discarded at the beginning. So that's the only difference. For partial Gutzwiller projection, I think well, then you have to keep all 4 states, and that's the only difference.
Right, but in terms of how well, do you have any experience yet with trying it out and seeing, how good are the wave functions? In somehow the spin models, you're getting pretty good wave functions, and it's really telling you something about the systems when you throw on DMRG and you see whether it matches. And, but I don't have a real sense of, it's like people have written down Gutzwiller type wave functions for Hubbard models and things. But, are they any good?
We haven't done any benchmark calculations for them, but it's definitely one direction which we would like to pursue.
Yeah. Great.
Thanks.
Please, Tarun, you please.
Great. Thank you for a very nice talk. I had maybe a somewhat tangential question. Does this approach give any insight into preparing Gutzwiller, this kind of wave functions with only unitaries and measurements?
Using what?
Using only unitaries and measurements, because recently there has been a lot of interest in, because both of these things can be done on a quantum computer. And to me, it seems like the way, if I think of it as a circuit, the way you're writing, it's not necessarily, the bulk is not necessarily unitary. Is it correct?
It's well, with our method, definitely it's not going to be unitary, because these are single particle correlation operators.
Right.
But of course, well, so first of all, you can make them unitary. For example, combine these guys and do singular value decompositions and pour the non-unitary part to the top, and then you can convert the whole thing into a unitary tensor network. Or the other way, you can think of well, so for example, the approach by Fisherman and Professor Steve White. So that in that way, you can actually convert the tensor. Well, you can prepare Fermi C or Fermi Gaussian states using unitaries, so that local unitaries. Maybe I don't have good plot for that. But basically, for each single particle orbital, you can always design two-side gate to disentangle the single particle orbitals. So actually, you can build a Gaussian unitary tensor network which has the mirror structure. Then basically you can prepare the quantum circuits for preparing fermionic Gaussian states, and in the end you can perform Gutzwiller projection. So that's a measurement.
And what will be the circuit, the shortest depth you can think of for the, let's say, Haldane Shastri wave function within this unitary circuit? Is it like or is it can be much faster than that, or
this I don't really remember.
That's fine. I think I don't want to.
Yeah, but I think, but I think basically here, if you start from here, basically you can do this block these guys and do singular value compositions, and then basically you just need capital N unitaries, layers of unitaries, right?
Right.
So it's maybe there are better ways, but at least we have a
suggestion by Ignacio Chirac and collaborators that if you combine unitaries with measurements, and Gutzwiller projection is like a measurement, sometimes you can do much faster preparation. And let's see. And I have one more question, but I will wait if other people have questions. I don't want to take up all the time.
No, please, Tarun, just go on.
Okay, thank you. About the, did you also study Gutzwiller projected Fermi surface, which has much larger entanglement in 2 dimensions? Did you also looked at that?
Well, so this so for this for this U1 gapless spin liquid for proposal, I think in this paper, I think they have a spin on Fermi surface. It has larger truncation errors, and additionally, other groups have also considered Gutzwiller wave functions for boson metal, and I think that has a Fermi surface. Definitely, it has larger truncation errors, but
I see. I was wondering, can you check the Vidom law and so on? Can you by changing all that stuff and changing shape of Fermi surface?
Yeah, I think it just depends on how large the cylinder is.
Okay. Thank you.
Thanks.
Yeah, please, Shang Hui-san, please.
Hello, thanks for the nice talk. I have a quick question. So I'm not sure whether I got the number correctly, but I think for conventional Monte Carlo method people, they could go up to size, say, more than 10 by 10.
Of course.
I would assume that it would be a little bit difficult for MPS. So
10 by 10, well, I think it depends on how large the entanglement is. But here, for example, this Hamiltonian, we could go up to 10 times 16, but probably the state is gapped, so it doesn't have too large entanglement.
Yeah, so I guess eventually the way to go is go, as you said, to the direction of using PEPs. So can you kind of comment on what's the difficulty, or if you guys have ever tried these directions?
We are working along this direction. We don't really have well, so this MPO MPS, this kind of evolution doesn't really generalize along that direction. So one has to think about something else. Like well, so I think you two once talked about Gaussian PEPs, and one could think of finding a Gaussian PEPs approximation for the non-interacting quadratic Hamiltonian, and then perform Gutzwiller projection on top. So that might be a approach. It's not clear whether it's good or not, but I think it's worth trying, and we are working along this direction.
Okay, thanks.
Thanks.
Maybe how I have another question. So at the end, if you look at the circuit of your free fermion wave function as an exact MPS, this looks very much like you would also do it for for a system that is solvable by the beta ansatz. It's and there it seems to be very hard to actually optimize the order in which you apply all these different bond dimension 2 MPOs basically. Do you know of any method by which you can actually construct something like these Wannier wave functions in the beta ansatz language? Because that would be very useful.
Yeah,
you can generalize this scheme of the way you build your MPSs as a product of these free fermions. Well, the way the beta ansatz works is exactly the same. If you look at the algebraic beta ansatz, it has exactly the same structure. But there we don't know of I think there is no notion of a Wannier mode, but maybe it's possible. Have you ever tried this?
Yeah, definitely. That's one thing which we have been working on, and in my group. And well, so first of all, this Wannier approach doesn't seem to work. So because this B operator, this MPO, actually they do not anti-commute with each other. So you cannot do arbitrary superposition to localize them. And then this Wannier approach seems to be very special for fermions. And we have been trying along the other direction by properly inserting some isometries in the tensor network. But for that, we need to understand the structure of a reduced density matrix. And but I have to say we don't have a working method right now. Yeah. But definitely, that's a very interesting question. And actually, this MPO MPS evolution is partially motivated by your beta ansatz paper.
I see that there's no urgent questions anymore. Is that correct? So if this is so, let's certainly thank Hong-Hao for this great talk, and let's see each other in 2 weeks. Thanks a lot.
Thanks.